Today is Tuesday, October 10th, 2017, and this is the NEERI Early Career Researcher Forum. This forum is intended to foster the exchange of ideas and be a platform of best practices for successful research. It is intended to highlight compelling research, build up the natural hazards engineering student community, and provide presentation opportunities. For more information, visit the NEERI website at designsafe-ci.org, where you can find links to the SimCenter and the NEERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today's presentation is by Andrew Sen, a doctoral candidate in the Department of Civil and Environmental Engineering at the University of Washington. His research investigates the seismic performance of pre-capacity design, concentrically braced frames, and provides practical guidance for their seismic retrofit. He is advised by Professors Charles Roeder, Don Lehman, and Jeffrey Berman. Andrew earned his bachelor's degree from North Carolina State University in 2012 and a master's degree from the University of Washington in 2014. He is the recipient of NSF's graduate research and the East Asia and Pacific Summer Institute's fellowships. He is the president of the EERI student chapter at the University of Washington, and the title of his presentation is Numerical Simulation of Concentrically Braced Frames Using OpenSeas. And so, Andy, if you'd like to begin, I'll pass it off to you.
All right, great. Thank you so much. Thanks, Matt, for the introduction. Again, my name is Andrew Sen, today I'm going to be talking about the numerical simulation of concentrically braced frames using OpenSeas. Okay, and it'll give me a chance to share a little bit about the research that I'm doing it, and maybe more importantly, how I'm doing it in OpenSeas. So I suspect many of you are already familiar with the concentrically braced frame as a lateral force resisting system, but it's a very common one in steel construction, particularly because it has high strength and stiffness. And we really design the braces to remain elastic under the design wind and earthquake loads. So the braces in effect are designed to prevent their buckling under those design wind loads and the earthquake loads computed from starting from the maximum considered risk-adjusted earthquake, dividing or multiplying by 2/3 and then dividing by the R factor of 6 for special concentrically braced frames. And so it's that final demand is what we're designing those for. Okay, and so because we're designing for such a high R factor, we're expecting significant nonlinear deformation in large earthquakes then. And the braces, being the primary lateral force resisting components, are dissipating energy in those large earthquakes through yielding and tension and then buckling and compression. And that means in order to accommodate that, we need to design the connections and the framing elements for those expected brace forces so that we can ensure that the braces act as more or less a fuse. So fundamental to the behavior of concentrically braced frames then is, of course, the brace behavior. And what we see is an asymmetric axial resistance, and that's largely driven by the buckling and compression that you see in the negative portion of the curve on the right there. And so braces fracture in tension at their midspan typically, and this is due to a low cycle fatigue issue in the plastic hinge region. And so in the top photo, I'm showing this local cupping deformation, as we call it, where you're really getting this high accumulation of tensile strains in that plastic hinge region in both tension and compression. So a little unintuitive, but because of the deformation compatibility of the brace section, the walls kind of cave in on themselves and the corners bulge out at that location, and you end up with a really high tensile demand, even when the brace is in compression overall. And then of course, the bottom photo is showing the brace after it fractures. So while this brace is buckling, okay, we have to design the gusset plate to accommodate that behavior. And it's either, you either get to design a fully restrained gusset plate, or what's more common, you design a gusset plate that is allowed to rotate. And we achieve this with either a linear offset like we see on the left here, or an elliptical clearance as you see on the right. Okay, and these are allowing the gusset plates to yield and sustain those really large rotations as the brace buckles out of plane. So the frame, okay, the braces are the primary lateral force resisting components, but the frame also provides substantial lateral resistance, even if you have simple beam to column connections. And this is largely because the gusset plates are stiffening the adjacent framing elements. Usually they're welded to those framing elements, and it's providing additional rotational restraints at those connections, and you can develop relatively large shears and moments in the beams and columns. And this behavior is thought to be rather important for collapse prevention of brace frames after the braces fracture. So the other component of this is we're analyzing brace frames using OpenSees. And OpenSees, again, I think a lot of you are going to be familiar with this already, but it's the open system for earthquake engineering simulation, and this is software that was developed by Peer with support from NSF. And in large part, it's a research-oriented numerical simulation software for structural and geotechnical engineering. I think sometimes you see it used in practice, but more often than not, it's really a research tool. So it's useful to know not only how to use OpenSees, okay, and that's basically what you might learn in a course or what you see on the website, but also understand what OpenSees is doing. Okay, and there's a couple fundamental principles to understand about how the OpenSees framework was developed. It uses object-oriented programming. So every object in OpenSees, whether it's an element or a material, a geometric transformation, whatever, it has a predefined role, but it's flexible, and you can add to those objects and manipulate them in different ways. So the other key component of OpenSees is that it's an open source framework. Okay, so it's really easy to get under the hood, so to speak, of OpenSees. You can go and actually look at the source code. It's not a black box. And if you're able to follow what's going on in the source code, then you can really understand what it's doing. So my take on OpenSees is that it's really a blunt instrument. We tend to use, in structural engineering at least, fiber-based line element models, sometimes in combination with lumped plasticity, whether they're zero-length fiber sections or springs. And I say it's a blunt instrument because, well, it's kind of imprecise in that matter. So there's no implicit simulation of local effects. So for instance, in steel, we're not able to simulate the local buckling behavior implicitly. Maybe we can kind of fake it, so to speak, with the material model. But there's no implicit formulation in there that's handling local buckling of those line elements. So the other issue is that, as in experimental research, the models that we develop in OpenSees are really highly idealized. They're kind of, we make a lot of simplifications, we make a lot of assumptions in terms of how they are modeled. So knowing that it is really virtually impossible to model all of the building components, including all the non-structural components, which inevitably affect the seismic behavior of a real building, we tend to ignore those in OpenSees. And then we make some approximations about how things are loaded in terms of the gravity loads, approximations for damping effects, perhaps due to those non-structural components. And so we got to understand, you know, it's a powerful tool, but it has its limitations, and we need to recognize that when we draw conclusions based off of it. So it is indeed powerful, right? And this is why so many people are using it. And there's a couple of reasons, and one is it has a relatively low computational expense compared to continuum models that, which are possible in OpenSeas, but for the most part today I'm going to be talking about fiber-based line element models. You might see continuum models from Abacus or ANSYS or LS-DYNA, something of that nature, but because of the low computational expense when we're doing these line element models, we're really able to run hundreds or thousands of ground motions with multi-story frames and really get an understanding of the dynamic effects of the full systems. So it's also, as I mentioned, because of its open source nature and the object-oriented programming, it's relatively easy to code, easy to perform parameter studies, and it's also relatively easy to hack. And I don't mean that in a malicious way, but you can open it up, you can modify the source code to meet your specific modeling needs, and as long as you're able to recompile everything, you're good to go. So OpenSeas are concentrically braced frame simulation, particularly special concentrically braced frame simulation, is pretty well mature in OpenSeas. There's a number of researchers that have really focused on modeling SCBFs in the past. There's work from Po-Chen Hsiao, from Karamansi and Lignos and Pachiuris and Steve Mahan that was done in the past 10 years or so. And the main focus of a lot of that work has been to provide a reliable prediction measure of brace fracture for the purposes of collapse assessment. Okay, and we'll talk about that in a bit, but I want to focus first on how we actually model the braces themselves, even thinking before fracture and just making sure that we can model the buckling behavior. And so what you see in the figure below is discretized brace elements, and these are usually displacement-based or force-based nonlinear beam column elements. Okay, and the reason why we discretize these and we provide this initial imperfection in them is to simulate the buckling effects. So OpenSeas doesn't simulate the small p delta effects, but it can simulate the large p delta effects using p delta transformations or co-rotational transformations. And so if we discretize the brace with multiple elements that all account for those large p delta effects, and we're approximating modeling of the small p delta effect, which is driving buckling. So we have the brace elements. These are composed of the fiber-based line elements, and then at the ends of the braces, we have nonlinear springs that represent those gusset plates, because as we mentioned, as the brace buckles out of plane, the gusset plates need to yield to accommodate that movement. And then between the gusset plates rotational hinge and say the work point of the framing elements in your building, we have rigid offsets, okay, to account for all the rigidity of that gusset plate connection and the beam to column connection where it's intersecting the gusset plate, okay? And so between those three different researchers that I mentioned, there's really two different approaches that have been used to simulate brace fracture. And I'll talk more today about the maximum strain range approach because this was developed at the University of Washington and we're generally more familiar with it here. But this was developed with a physical significance focusing on that plastic hinge region in the brace, noting that in both compression and tension, the strains are accumulating in that region where we have local cupping if we have a square HSS brace. And so in OpenSeas, we sort of look at something, a strain measure that's not exactly real because we're not modeling the local cupping deformation. We have to have plane sections to remain plane in OpenSeas. So we have kind of a pseudo strain, and we use the strain range between the maximum positive and the maximum negative strain across the entire brace history to trigger fracture. And so this is the maximum strain range approach. I abbreviate it MSR here. And you can see that it's calibrated by Pochen in 2013 based on some properties of the square HSS brace. So it's based on the width to thickness ratio, the global slenderness ratio, and the ratio of the elastic modulus to the yield stress. And the other approach is really a fatigue approach that was developed at Berkeley, and it's uses a Coffin-Manson relationship and a modified rainfall cycle counting of the strain amplitudes in order to trigger fracture in that case. Okay, and again, you can go back, and Caramansi and Lignos calibrated some of those parameters for different types of braces in their paper. So the way these generally work are as material wrappers. So both max strain range, as I'll call it here, and fatigue are material wrappers. And so the wrapper, the way I like to think about it is that it spies on the inner material. Okay, so maybe that inner material is steel O2, maybe it's something elastic. It can really be anything. And the max strain range material is what communicates to the outside world, which are the sections, the elements, and all of that. But the behavior is still dominated by what's happening inside with steel O2. So when a critical point is reached, so say you've reached the maximum strain range or you've hit your fatigue criteria, the wrapper performs some sort of action. And so it either overrides the behavior, reduces the stiffness somehow, and we'll see that maybe we can do more with that. And so that's actually simulating fracture at the fiber level then. Because we have these fiber-based line elements as our braces, each one of those fibers has its own version of steel O2 and its own version of the maximum strain range wrapper. And so you can actually get fracture on a fiber by fiber basis, and that kind of simulates the brace tearing or partial fracture that you might see in an experiment. But truth be told, the modeling capabilities are really not that precise, even though it might look like we can simulate those things pretty well. So as far as the frame and the gusset plates go, there's work that was done by Pochen again, Pochen Xiao in 2012, that demonstrated the importance of different frame modeling assumptions on the global behavior of the brace frame. Okay, and so he has three different models here, a pin-connected model for both the beam-to-column connections and the gusset plate, a rigid connection model, which is in the center here, and then a proposed model where we have rigid offsets for the beams and columns and gusset plates, and then he's using a rotational spring with the plastic capacity of the gusset plate for the gusset plate model. And so you can see moving from pins to rigid, we go from something that's underestimating the measured response from an experiment to overestimating the measured response. And then eventually you're able to calibrate something that looks a lot closer to the actual experiment once you get into the proposed model with the rigid offsets and the gusset plate spring. So that's really the state of SCBF modeling as we see it today. And it's unfortunately not the end of the story. So SCBFs have really only been around since about 1997, at least in the form that we know them. And capacity design has really only been around since about 1990. And so there's a large quantity of older CBFs in regions with high seismic risk in the US. Okay, so places like the West Coast, places like maybe parts of the Midwest, they all have these non-ductile concentrically braced frames, or NCBFs, as I call them. And so these were designed really with just the strength and stiffness approach and not much consideration for ductility of the frame. And so there's a pretty large concern about their seismic performance. From past earthquakes, okay, we have a limited understanding of what happens, and you can see some high instances of brace fracture in some frames. The left-hand photo is from a building that was damaged in the Northridge earthquake. And then on the right, you see a connection issue with that plate connection with the double angle braces that was damaged in the Tohoku earthquake. Okay, so there's some limited understanding, but we don't really know at a broader level what the impact of these different deficiencies are. And so what are those deficiencies? Well, I said there was no provision for ductility in the frames. And if we compare the present design criteria to a pre-1988 design criteria, you see a lot of differences, and a lot of the differences are, well, maybe there's no restriction or no requirement for something. So there's no restrictions on the brace configuration, for instance. There is a restriction on global slenderness. There's a restriction on local slenderness, but it's really nothing compared to what we have today. It's just a basic compression member local buckling limit. Gusset plates didn't have to accommodate end rotation. They didn't have to develop the maximum or the plastic moment capacity of the brace. And then the welds did not have to be demand critical. They didn't have a minimum toughness, so they're prone to fracture after just a little bit of cracking. So this is just an example. So some of these are going to be local or component deficiencies, like the width to thickness or local slenderness ratio of the brace. Noting that as we increase the local slenderness ratio, we're really decreasing the fracture life of the brace after it buckles, because we're intensifying that local cupping deformation that you would see at the midspan if you have a square HSS brace. Okay, and then other problems are more systematic in nature. So all of the frames here would have been compliant in terms of their configuration for an NCBF. We removed K-bracing for SCBFs, and then we have some pretty severe requirements for chevron brace frames in SCBFs. And so in the past, we didn't have any of these restrictions. So their performance and the way they actually look, if you're able to look at the frame itself, are very different. So this really motivated, these big differences that we see really motivated my current research. So there's an expectation of poor seismic behavior, but it's truthfully not well understood. I mean, you see some evidence from past earthquakes, but you know, maybe not enough. And we know that there's a substantial building stock of NCBFs. We know that there's these shifting expectations of seismic, or shifting societal expectations of seismic performance and resiliency in communities on the West Coast especially. And then there's really limited guidance for how you would actually retrofit them. So this triggered a large experimental research program and companion numerical analyses that I'll talk about today. And so these experiments are really providing solid evidence of the behavior of some of these NCBF, how they're behaving under different deficiencies and so forth, but they're really constrained in terms of the scope of the experiments due to really practical concerns of cost and facility limitations and so forth. So the numerical analyses then provide a near limitless scope, which can be a real problem because you can do anything. And so you have to be careful to stay grounded in reality and do work that's well validated by the experiments that you're able to calibrate. So there's two main questions here for the NCBFs then. If we're going to think about them as a society, we want to know what the benchmark seismic performance is of the typical NCBF. And that should answer the question too, if they should be retrofitted or not. Certainly, I think there's an expectation that they need to be retrofitted. So in those cases, what are the circumstances of the retrofit and how do you actually perform it? So these are the research questions that I'm trying to answer. And so the overall approach is pretty vast, and it spans something like 5 years now, and I think 5 different graduate students, including myself. And it started off with an infrastructure review. So we looked back at some of the drawings to understand what these frames actually looked like. We know what the code requirements were, but it's important to see how they were actually built. And that went on to develop specimens for sub-assemblage testing. And then everything after the sub-assemblage testing is really numerical analysis. So we want to be able to simulate those tests. We want to expand those tests into full building models and then make some decisions about what we think the benchmark NCBF performance is and how we think retrofits should be performed. So in the infrastructure review, we had drawings from 12 low to mid-rise buildings from the US. There's really a wide array of different connection types and different brace types, different framing sizes. I mean, it runs the whole gamut. And so it makes doing the experiments and doing the analyses a little bit difficult because we know that there's such wide variation. But we tried to focus on a couple of the connections here that we think were more common. And so that was all done based on just what we had available. And when we check the connections, we want to look at the demand capacity ratios for the different limit states and geometric limits that we have. Okay, and so there's 3 different categories here that I'll talk about. We have yielding mechanisms, okay, so things like yielding of the brace and the gusset plate, and even of the beams and columns are all actually beneficial. And so if we see a yielding mechanism with a DCR of close to 1, okay, which would, if it's 1, then it's actually not code compliant because we have resistance factors and that lower the effective resistance that we're designing for. But if we're close to 1, we think maybe it's not a concern. On the other hand, we have failure modes, and there's a ton of these that could occur in any given brace frame. And we really want the DCRs to be much less than 1 in order to feel good about their presence in the frame. So these are things like net section rupture of the brace, bolt fracture if we have a bolted connection, weld fracture with welded connections, and even fracture or block shear rupture of the gusset plates. And the third constraint we want to look at is geometric limits. So things like brace local slenderness that I mentioned before. If the brace is highly locally slender, then it's going to have a much lower fracture life, and that's going to hinder the seismic performance. And then we also want to look at the clearance to accommodate the end rotation of the gusset plate. So we set about doing some sub-assemblage testing, and there's 18 tests that were performed at the University of Washington, 4 tests that were done at the National Center for Research on Earthquake Engineering in Taiwan. Okay, and I just want to highlight some of the results for those. And you see that a typical NCBF has a drastically reduced deformation capacity than an SCBF. And so the deformation capacity really being defined as when do we lose significant lateral resistance. So for an SCBF, as is in gray in the figure on the right here, we have a drift range capacity, so the maximum positive drift minus the minimum negative drift, or that total range between the two, of about 5 or 6% for the SCBF. And for the NCBF, we get something on the order of 1.5%. Okay, and so then this particular specimen, we had the premature brace fracture because the brace was locally slender, and therefore we're really fracturing the brace very early on and losing significant lateral resistance. So this is all driven by that local coupling that you see in the photo there. Of course, there's a bunch of different failure modes, not only local coupling of the brace, but also fracture of the gusset plate to beam weld, as you see it in this figure here, and then also of the bolts on the gusset to column connection. Those are also subject to fracture. And then you might see something like this, where the brace to gusset plate connection fractures either due to net section rupture or potentially weld rupture. So all of these, under pretty typical demand to capacity ratios that we saw in the infrastructure review, all had a drift range capacity between 1 and 2%, which is really unacceptable. So for the most part, we think that you should be retrofitting these frames. And so we tested a bunch of different retrofits, and you can see that it can change the behavior drastically. So in this case, we're looking at a retrofit where we just replace the non-ductile brace, the high locally slender brace, with a smaller brace. And in turn, we still have a fracture of the gusset to beam weld connection, but the brace hangs on, the gusset plate hangs on through the column connection. We're able to develop significant resistance through that brace still, and then eventually the brace is able to fracture, okay? And so this is a much more ductile behavior than we saw with just the regular NCBF. And now by retrofitting it, or significantly improving the performance, but it may not be to the level of an SCBF. Okay. So I just want to show a video here, and hopefully it comes across well. It's a compilation of photographs, so it's not supposed to be smooth. But I think what you'll see here is that the behavior of these NCBFs are really quite complicated, much more complicated than the SCBFs. And this is going to present some pretty significant modeling challenges as we move forward. And so you can see significant yielding of the gusset plate, a lot of rotation at that beam to column joint after the gusset to beam weld is fractured. Okay, and so, how do we model this? This is nothing like what we've seen with the SCBFs. Okay, so we know that NCBFs are now prone to premature fracture depending on their limit state and DCR. And we know that retrofitting the NCBFs can significantly increase the drift capacity, but can cause some pretty complex behavior that we need to model. So there's other issues at the system level. We can have yielding of the beams in the chevron configuration. That's entirely possible. And there's other things that we're just not able to simulate experimentally, like column buckling, due to really practical laboratory limitations. So in general, the NCBF behavior, we can tell, cannot be simulated using the existing SCBF recommendations. But because there's still brace frames, we want to build off of those recommendations here. So the first step in understanding how to model the behavior of these NCBFs was really to try and simulate the experiments. And so here's on the left, a schematic of the actual experiment that was performed in the lab at the University of Washington. And then on the right, you see a schematic of the OpenSeas model composed primarily of line elements and zero-length spring elements. It's modeled pretty much similar to the SCBFs, but we find that we need to make some changes here. So there's complex behavior, especially at the brace to beam column joint, as we saw in the video. And so we need to be able to handle that somehow. And then we also have all these different failure modes that could occur. We have premature brace fracture, okay, and this is what we call primary failure mode, because after that occurs, we lose the axial load path to the brace. We have brace to gusset weld fracture, which is another primary failure mode because, again, you're losing that load path. And then we have gusset to beam and column weld fracture, which is either a primary failure mode or a local failure mode, depending on what happens in the post-fracture range. So the gusset plate could tear off entirely if it's welded on both sides, but potentially if it's bolted, you could get some significant deformation capacity through those bolts. Okay, and so in order to perform these simulations, we need a strategy first for simulating their behavior. And then after we feel comfortable with our simulation approach, we need a method for predicting that behavior in the future. Okay, and that's going to be important as we try to expand our experimental simulation models out into a full building model. Oh. Okay, so the first step that I saw here was really to generalize the maximum strain range model that was developed by Poch and Chow. And so he actually gives the source code for his model in his dissertation. So that's a really great place to start. And so I examined that, but in the end, really needed to relearn C++ so that I could modify what's going on in OpenSeas. Okay, and this is done in Visual Studio. I found that was the program most helpful to me. And so here, if we can start to hack, we can start to change what was already done. We don't need to reinvent the wheel. Okay, this is like the beauty of having the open source framework, is that we can go in and modify things to suit our needs. And in doing this, we need to make sure that we're citing the previous work appropriately and giving credit where credit's due. So I made some major changes here. to the maximum strain range model. I generalized it so that the inputs for the fracture deformation range were input directly rather than through KL over R, W over T, and E over FY. Those were the brace section and material parameters. And the way Po-Chen had written it, you input those and then it calculates the maximum strain range you should be using automatically. So now I'm saying, well, let me just give it the maximum strain range I want it to use. I added the ability to define a post-fracture stiffness as a ratio of the initial stiffness. Okay, sometimes there's convergence issues. So if you have a post-fracture stiffness, so this is what happens when the brace or the fiber kind of lets go. There's a residual stiffness that you need for convergence, but if it's really low, you may run into problems. So by amping up that initial stiffness to a reasonable level, you may be able to improve your convergence performance. And then I also added the ability to remove elements upon fracture, okay? And so this was a more complicated behavior. Actually, this one took the most time to code, but we can go in and when the maximum strain range fracture is triggered, instead of just simply removing the material, we can remove different elements, okay? And this may be useful. So now the use of the maximum strain range material, as you see here, you'd be able to input the tag of the elements, or sorry, the tag of the material, the tag of the previous material that you're wrapping, and then of course the maximum strain range limit at fracture. And then there's the options here for minimum and maximum strains or deformations, the tangent ratio that I talked about, and then the different elements that you want to be removed once fracture actually occurs. Okay, so the other part of this was now we're making the models relatively complex, and coding the models by hand and Tickle is just, it can be a real pain. It's not always easy. Tickle itself is usually less intuitive to users. They're less familiar as a coding language than MATLAB or Python. And so I really sought out to change how I was interacting with OpenSeas. What happened was we developed a framework in MATLAB, and there's a similar one in Python that this is based off of. And the links to these are at the bottom of this slide here. And what we're really doing is creating an application programming interface in these languages to actually build the Tickle models. And so we're managing a user-side database in either MATLAB or Python. And from there, we can interact with the database. We can create objects. We can edit objects, all without writing the Tickle code right away. And then at the end, we're able to tell the program to write the Tickle code, and it kind of translates all the work that you did in either MATLAB or Python into a Tickle file that you can run in OpenSeas. Okay, and so this is what we call an OpenSeas API. And there's two different GitHub pages here, whether or not you're interested in MATLAB or Python. So with that said, there's a couple of different options here that you might use for pre or post processing. There's MATLAB, Python, and probably less familiar, Julia. And they all have their pros and cons, and my advice really is to do what feels good to you. I mean, if you're familiar with Python, then you should probably use Python. If you're familiar with MATLAB, you should use MATLAB. And Julia is maybe a language for the future here, but really not mature enough at this stage to use as a reliable pre and post processing tool. So that's my comment, MATLAB versus Python. I think some people can get pretty defensive about it, but really kind of do what makes you happy. Do what makes you be productive as a researcher. So the way I'm using this OpenSeas API, I'm using MATLAB then, and there's a couple of benefits to doing this that I already touched on a little bit, but all relevant information is stored in this MATLAB object now, so I can interface with it using MATLAB. I don't have to think about using Tickle really. And the user does not need to keep track of any of the tags that you need for the elements or materials or nodes. All of that can really be automated by MATLAB, and all we need to think about is then our variable names in MATLAB. And then the other nice thing is everything is editable after it's already created. So we can create a node and then go back and think about, well, for some reason I need to offset the node. Well, I can do that in MATLAB, and then in the tickle file, it'll just be written directly as the final version that you produced. So the other component of that is the order that we define different objects doesn't really matter as long as it's logical. And then the code will go back and reorganize all of your objects and print them in tickle in a form or an order that makes sense. So not defining the elements before the nodes and all that stuff. So for example, what's really beneficial about this, if I want to create a max strain range element or max strain range material with element removal, okay, I might create the initial material, and this is everything that I'm doing in MATLAB. Like say I'd create the initial material in MATLAB, create the max strain range material, okay, and this is going to reference that initial material. Then I'm going to create all the elements later on, but then I'm going to go back and say, well, now that I know what elements I have, and they've already been assigned these arbitrary tags by the system, I want to go back and say, well, I want to use this element to be removed in the max strain range material. Okay, so I don't need to know any of the element tags a priori to create the max strain range material with element removal. I can kind of play around with the order of operations for how I'm defining these different parameters. So without using MATLAB or Python or whatever as intermediary, it's up to you to keep track of all those material tags, element tags, node tags, and that's just a lot of numbers, and it's really easy to make a mistake that way. So my philosophy here is just let the program, let MATLAB assign arbitrary node tags and all that stuff, and then I'll just worry about what I call the nodes. So if I have nodes that are work points, I know that they're work points 1, 1, 1, 2, 1, 3, 1, 4, whatever. But I don't really care about the tag. I might care about that matrix of work points that I have created in MATLAB. So the other component of this is helpers and utilities. So you can have these additional functions that perform repeatable processes in the OpenSea's API. And so one of those would be tag numbering. So we can check if a tag is available and then assign it if it is. Brace helper, so anything, a brace or beam column helper that creates all of the nodes and elements that you need for that certain section. You can just provide some initial inputs like I have shown at the bottom here. This is a screenshot from MATLAB. And I can say, well, NEL is the number of elements. I want 16. I want 5 integration points per element. Providing initial imperfection. Maybe there's an eccentricity of the brace. And I can just provide all this information and as well as all the other relevant information that you would need for creating a line element. So the section, the geometric transformation and all that. And then the helper goes in and constructs that brace for me. So I don't have to think about all the crazy geometry that might be going on, especially if you have a 3D system. So in the end, you're actually able to use MATLAB or Python as a one-click tool for doing your analysis. You can pre-process, process, and post-process all in MATLAB. So you can build the model in MATLAB with that API. You can run it through the command window and then load and plot the results all with one click. So it's really convenient in that respect. So I'll just go through quickly here. So the brace, so let's talk about the different connections and how I'm using the generalized maximum strain range material wrapper to simulate these MCBF connections. And so if I have a brace to gusset weld fracture, I'm going to model the brace to gusset weld using some recommendations for the load deformation behavior from the AISC steel construction manual, actually from the specification. And from that, I can figure out the load deflection behavior, okay, and I can model that with just a simple multilinear model, and then have a maximum strain range wrapper at the ultimate deformation of the weld. Okay, and I can go through and actually simulate that behavior in one of the tests. So here in gray is an experimental result, and then in blue I have the simulated result. Okay. A more complex behavior is in the gusset to beam weld fracture. So in this case, we have really a local failure mode where the beam to gusset plate connection disconnects, and then we have to figure out what happens after that. And so first of all, we have a criteria that we've calibrated for that fracture to occur, okay, and it's based on the clearance of the gusset plate and the demand to capacity ratio of that weld. And then we can use that to trigger fracture of the gusset plate, and then we can remove some elements in order to basically unstiffen that connection. So I'm removing a rigid element at the beam to column connection, and I'm removing a rigid element on the brace to gusset connection, because now I have a relatively free gusset plate. I have less restraints at the beam to column joint, and I should be modeling that if I want to model the NCBF accurately. Okay, and so here's an example where the whole gusset plate disconnects, and there's really no residual force left in the brace. So everything you see after the gusset to beam weld fracture is frame action. Okay, and then this is a case where we have some reserved connection strength, where you're still developing load in the brace, and then eventually, because of the large compressive deformations that the brace is still seeing, you're able to fracture the brace even analytically. So there's another set of tests in Taiwan that we conducted, and you have a pretty similar model with the line elements and the gusset plate springs. And so I just want to show that, yes, we can simulate these effects as well. And then the real goal is to get to nonlinear response history analysis. So we're interested in the seismic performance of NCBFs and retrofit NCBFs. And so we might want to look at how they perform at certain hazard levels. So now we have a need to run a bunch of different analyses with a bunch of different ground motions, and we have to also extrapolate our models from those experimental simulations out to the building frame. Okay, and these two tasks are really streamlined by using the OpenSea's API approach, because we've sort of simplified how we're building braces and all that stuff. And then also, this is a problem that lends itself to high performance computing. So I just want to say we have 4 different frames here with 3 and 9 stories and different bracing configurations. And this is what the full building model might look like, okay? And it's a pretty detailed model. We've even discretized the columns here to simulate buckling of the columns, because the columns may be weak in an NCBF, even though we couldn't test that experimentally. And there's a lot of details to this model, but I just want to show what we're capable of when we're doing this OpenSea's API and high performance computing combined approach. And if we can take all these different ground motions, because we have information in the OpenSea's API about the node locations and everything, it's really easy to build this simple preview model and then adjust it for the different deformations that we're recording in the analysis, okay? So as far as high performance computing resources go, from our end at the University of Washington, we have our own supercomputer called HIAC, and we have nodes from our department, and also we have a high performance computing club that has access to nodes, and so that's a pretty unique role that they play. And so, if you're at your own institution, you may see if these resources exist, but if not, then there's Stampede and TAC at the University of Texas, and you can interact through Stampede with either a shell or through the Design Safe Discovery workspace that's linked there. And so you have access to these high performance computing resources, even if they're not at your own institution. Okay, and these are just some details about how you actually do this. So if we have a bunch of different ground motions that we want to run, from the work that I'm doing, it makes sense to run a bunch of jobs at the same time on the same node just utilizing all of the different CPUs. So this is sometimes called high throughput computing. Okay, and so you need to make a batch file with all of your different analyses or jobs that you want to run, and then schedule it to run with Slurm if you're on Stampede. So this is just illustrating the scale of the problem. So if we have all these different ground motions, maybe we have 60 total acceleration records for each hazard level, 5 different hazard levels, that's 300 analyses per building. And so that's not something that you really want to be doing on a local machine. Right? You want to be able to go onto a supercomputer and do those analyses quickly. So I just want to show a quick result here from an NCBF, okay, and this is a 3-story NCBF with high B over T braces that are expected to fracture prematurely, and then different gusset plate to beam, or brace to gusset plate weld connection DCRs. And so now you can see there's really well over 1,000 analyses represented on this plot, moving from 5 different hazard levels and 6 different connection DCRs. And you start to see some pretty clear results that the NCBFs are highly deficient. If we think about what the expected performance of a modern building is from ASC 7, we say that in a 2% 50-year earthquake, there should be less than a 10% probability of collapse. Well, if we look at the blue line here, everything, even if the connection DCR is below 1, so it's not deficient, everything is well above that 10% limit. So, of course, there's other issues with OpenSeas that I haven't talked about today, the issues with damping. There's different choices on what to do. Issues compiling OpenSeas if you're making these modifications. You're either doing it in Visual Studio on Windows or maybe on a Mac or a Linux machine using Make. And then there's the age-old issue of convergence. So my real advice with respect to that is to talk with people in your offices. More often than not, they've probably experienced the same problems you've had before. And so get their perspective. Ask questions on the OpenSeas message board, and then if all else fails, or maybe the first thing you should really do is read the OpenSeas wiki and understand the syntax and what it's trying to do. So to summarize, SCBF modeling procedures are really well validated in OpenSeas at this point. It's the NCBFs that are the real challenge right now. And this is because of the premature and local failure modes that develop. And so the preliminary results that are now being built off of those experimental simulations have a potentially high probability of collapse in severe earthquakes, but there's really more to the equation. We need to look at multiple story heights, like I had mentioned, at the prototype buildings, different configurations, and then the interaction between those different deficiencies. But as far as OpenSeas goes as a tool for doing that research, it's really fantastic. You can take advantage of the transparency of OpenSeas, the open source nature of it, and how adaptable it is because you can see the code. And then taking advantage of the OpenSeas API approach to where we're really getting kind of hands off with Tickle and letting the machine write the Tickle code can really help you avoid mistakes and work pretty quickly to change your models. And then of course, if you're able to access high performance computing resources, that can be a real benefit to increasing your research output. So I just want to acknowledge the funders of the research that I've been conducting. Largely, these people are funding the experimental research from NSF and American Institute of Steel Construction. I want to acknowledge my advisors and Professor Laura Lowe's, who invited me to give this talk today, and then the former students that helped on this project, Dan, Molly, Ryan, and Marcia, who are doing bigger and better things now, and Nassim Rafi at the University of Washington, who's my main go-to person for OpenSeas advice. So that's a bunch of references here, and that concludes my presentation. So if you have any questions, I'd be happy to field them.
Thank you, Andrew. That was great. At this time, we'll open the question and answer session. Attendees are reminded that questions should be submitted through the chat panel and sent to the moderator. You'll remain in listen-only mode for the question and answer session as well. So the first question, Andrew, is does the MATLAB API make troubleshooting more or less complicated in OpenSeas?
So from my perspective, the MATLAB API makes it less complicated. I'm able to go in and see exactly how I've defined the nodes and elements before I've even built the model or even written the model in Tickle. And so, you know, I think because of those plotting capabilities that are native to OpenSeas, it does make the troubleshooting quite a bit easier.
Okay. If you could maybe jump to slide 12. There's a question regarding the parameters that are required from going from the simpler to the proposed model for the braces. And questions about how well are those parameters characterized?
So if you are able to look at this paper by Pochen in 2012, he does give pretty clear recommendations on the size of the rigid offsets for the beams and columns, and clear recommendations on how to formulate that gusset plate rotational spring and what parameters you should be using. It's really just based on mechanics for the gusset plate and the Whitmore width of the gusset plate. So it's relatively straightforward and backed by physical behavior. So that answers, yep.
Okay, and then what properties do you recommend for the rigid elements at the gusset plate locations? And what element type do you suggest?
Yeah, so in my experience, what I found works well is to use elastic beam column elements. And you want to make sure that you're multiplying the stiffness from the base case to a relatively large number, but not too large, so as to cause convergence issues. So I think, even if you multiply the stiffness of the element by a factor of 100, that's plenty to model it as rigid.
Okay. And then some questions about the element removal command.
Yeah.
I guess maybe one question is around the recorders associated with those elements. Does the element remover command take out recorders or handle the recorders at all?
It's a good question. So I haven't actually made recorders for those elements that I've been removing.
Okay.
But I believe because the element no longer exists in the domain, the recorder will just go blank and not record anything. But I have to say I haven't tested that case.
Okay. And is there a specific name for the element removal command?
There is a native command in OpenSeas. If you're doing it from the source level, it's a little more complicated, but I think the native command is on the wiki. I don't know the exact name of it though.
Okay. So then another question is, how would you rate the convergence behavior of the proposed brace and connection model under large amplitude ground motions?
It's generally okay. It certainly adds complexity to the model and lengthens the time it takes the model to run. But I'm finding that at least in these simple cases where I just remove or I have a brace to gusset weld fracture simulation, it doesn't really change that much. And in fact, because I'm removing the load path to the brace and providing some supplemental but really low stiffness, convergence is actually a lot easier to achieve after that fracture occurs. So
around the convergence issues, how did you solve the problems you encountered? Any suggested solutions or strategies?
Yeah. So my suggestions would be to, it all comes down to your analysis algorithm. I know there's a bunch of different algorithms that people use that are floating around to where you're reducing the time step or changing the algorithm itself that's used in OpenSeas. my suggestion would be to really just play around. I mean, it's going to depend on your specific problem. You know, sometimes increasing the maximum number of iterations is good, but sometimes that can just cause greater issues and really slow your model down. What I suggest is when you're reducing time steps is to take the reduced time step and do more than one. Don't just do one and then jump back up to your original time step, because more often than not, you're going to have another convergence issue and you're going to have to go down to that smaller time step. So if you stay in that zone for a little bit longer, I think that's what the one of the variable transient solver in OpenSeas does is it spends some time down at the lower time steps and then goes back up once it's successfully converged for 10 steps or so.
Okay. Regarding the initial imperfection that you're adding for the brace, is that a constant value or does it vary by time?
The initial imperfection is seeded in the brace, so it's the actual node locations that you provide. And what's typically done is to use 1/500 times the length of the brace. And that's pretty close to the limits for imperfection in the steel manual. And so it approximates the buckling equation pretty well too also.
Okay. Back to a question about the rigid elements you're using.
Yeah.
What is the area of the rigid element at the brace location?
Yeah, so the rigid element can have really any area. You're worried about E times A, right? Is the rigid stiffness. So if your E is very high, it doesn't matter if you've retained the original area of whatever section that is. You just want a high E times A.
Okay. And the last question, would you maybe jump to page 49?
Yeah.
Slide 49.
Okay.
And the question is, how did you, So it says, how is the clip on page 49 made? But I don't see a clip on page 49, so maybe
it's this one?
Yeah.
Yeah, so this is made in MATLAB, and if you go through the documentation there, there's an option to write video, and basically you're just layering a bunch of different, well, not layering, but you create a figure, and then you go in and using the deformed location of all of your nodes that you recorded in the analysis, all you need to do is change the locations of those nodes in each frame of the video. And I think there's a get frame command and there's a write video command in MATLAB. And so it's all possible. Something of this level, you really benefit from building the model in MATLAB first, because you have all the node locations inherent in your database already, and you don't have to go and figure out translating what you wrote in Tickle back to MATLAB. You just have it in MATLAB already. So that's an area where doing the pre and post processing in the same program is really helpful.
Okay. Well, we're at the conclusion of today's Early Career Researcher Forum. On behalf of the attendees, thank you, Andrew, for taking the time to share your research. To the attendees, thank you for your participation and questions. Please check the EERI website and check your inbox for emails from announce@designsafe-ci.org that will have registration links for additional upcoming webinars in the Early Career Researcher Forum and the Natural Hazards Engineering 101 webinar series. Thank you for attending today's forum. And again, thank you very much, Andrew.
Thank you.